So we are going to talk about the factors affecting persistence and the efficacy of soil applied herbicides. So we'll start with the persistence. What is it? It is the length of time the herbicide is present in the soil being active. If it is active for at least 3 to 4 months, then the activity is desirable. It can protect the crops by killing weeds for that period. But if the herbicide stays for 1 year or more, it becomes undesirable because it starts interfering with the crop rotations. Now let us just look at the pesticide use in agriculture. Herbicides and insecticides, fungicides have a potential to pollute the environment. For instance, we now have pollution problems caused by DDT, which was detected in water bodies, birds, animals by Zaranyika and Makubaro studies in 1996. Chikuni and Nachi also detected DDT in human milk. This is a pesticide which is now in the ecosystem. So, because of these issues, there is really need to decrease the use of pesticides. So, there's this trend where we are moving towards organic farming by reducing the pesticides. But later on, you'll find out that pesticides may not also stay in the environment, depending on the nature of the pesticide. Now, the herbicides with a potential to persist in the environment are as follows. We want the pesticide to be in the environment to do their job for a certain period. But if they continue to stay in the environment, then they become pollutants. We've got triazines, atrazine, and simazine. They have the potential to remain in the environment for more than a period which is not necessary, which is unnecessary in terms of agricultural production. Dinitroanilines, we have got pendimethyline, stomb and trifluorine. Phenylureas, we have got diuron. Uracil, we have got bromacil, Trek, chemical X. Anyway, bromacil is used along railway lines to protect the railway tracks from the vegetation. So, along railway lines, maybe long persistence is desirable because this is not agricultural fields. Imidazolinones, we have got imazapa, acinar, imazitapa, imazaquine. Sulfonylureas, we have got chlorimuron classic, nicosulfuron accent, others like command, chromazone, which is used to control weeds in tobacco. But we haven't had persistent problems from chromosome. Probably in this country, it could be only atrazine, which sometimes give persistent problems. Now, what causes the herbicide to remain in the soil could be the soil properties themselves. For example, we have got morillonite clay minerals, uh, kaolinite clay minerals, which can actually absorb the herbicides. We've got also organic matter with COOH and OH functional groups, which can absorb the herbicides because there's the presence of negatively charged surfaces, which can attract positively charged particles from herbicides. So the cation exchange capacity of the soil may be important in determining persistence of the herbicides. Now, there are two things on the herbicides. I was talking about persistence. The other important issue is efficacy. Efficacy is the effectiveness of the herbicide in controlling weeds. Uh, we can have good weed control, which is desirable, or it can be poor weed control, which is undesirable. So, what we want to talk about is what happens when we spray the chemicals to the soil. So, the question is what will happen to soil applied herbicides after spraying? So, I'm going to give you the answer immediately. So, this is what can happen to the pre-emergence herbicide when it is applied to the soil. Number one, the herbicide can be reached. Number two, the herbicide could be lost into the atmosphere via volatilization. Number three, the herbicide could be broken down by microbiological activities. Now, microbes possess some enzymes and they can facilitate phase one, phase two, especially phase one and phase two reactions. Then in number four, we could have plants which can actually remove herbicides from the soil by absorbing them, translocate them, then they can subject these herbicides to herbicide breakdown via phase one, two, and three reactions, which we have already discussed when we were talking about selectivity. The other issue, which is number five, is adsorption by soil colloids. So, depending on the nature of the soil, there could be clay minerals, organic matter, which can adsorb these herbicides such that they may not become available. Then we move on to six, where we have the activity of sunlight which can trigger photochemical decomposition. So there are some reactions which are aided by the presence of light. Or it could be the last, where you have a straight test tube kind of reaction. You apply herbicide to the soil, there's an immediate chemical breakdown where the herbicide is converted to various substances which makes it inactive. So in summary, this is what can happen when we apply herbicides to the soil. So what we are going to do is to discuss these processes one by one. So we talk about physical processes. Number one, leaching is one of them. If we apply the herbicide to the soil surface, it can either be moved downwards. And the extent to which the herbicide can move downwards depends on its solubility. Solubility is the ability or the degree to which the herbicide is dissolved in water. Here I've got a list of herbicides with their solubility properties, which are in parts per million. The most easily soluble herbicide is dicamba, which is used to control weeds either in maize or wheat. It has got 720,000 parts per million. That is the most soluble. And we have others which are in between. Probably the least soluble here could be pendimethalin, which is not easily moved. Even metribuzin cannot also easily be moved. We know pendimethalin and metribuzin facilitate depth protection. Metribuzin in soybean and pendimethalin in maize. Of course, these other herbicides can be applied pre-emergence. Other factors are involved. And trifluorine has to be incorporated. So apart from solubility, you may find that there are other things which are involved for herbicide. For the herbicide to leach. So leaching is the movement of the herbicide downwards through the soil profile. It is desirable when it takes the herbicide to the weed zone, where we can have a positional selectivity or depth protection. If it is undesirable, then the herbicide is reaching the crop zone and there is a loss of positional selectivity leading to crop damage. Like what can happen if we apply Sengo or metribuzin in soybean, then we receive a storm or a lot of rain, which can leach the herbicide. So this diagram is explaining positional selectivity or depth protection, which we have already done. So I'm not going to spend much on it. I want to talk about the factors affecting leaching. It's the amount and intensity of rainfall. If it is very high, it can cause leaching. Soil texture, amount of clay and organic matter are also important because they tend to absorb the herbicide. I will talk more about adsorption later on. Now, adsorbed herbicide may not leach. Ionization properties of the herbicide may also affect the ability to be leached. For example, positively charged herbicide can be attracted to the clay minerals and reduce its leaching properties. However, there could be herbicide loss through surface runoff, which can depend on the rainfall amount, rainfall intensity, and the erodibility of the soil. In other words, if there's a lot of erosion, you can have the removal of the herbicide outside the area where it is applied, and it can cause some damage elsewhere. We can actually demonstrate under laboratory conditions or glasshouse conditions how the herbicides can get leached. Now, what you need is a plastic pipe with some holes on each side. You may close these holes after putting some soil. You put a certain dosage of the herbicide. Make sure the pipe is perpendicular. So you apply your herbicide, you apply a certain amount of water so that the herbicide is leached through the pipe. You can do it for a few hours, probably to a day or several days. Then you lay the pipes horizontally, and on the walls you can plant a sensitive crop, like in this case, cowpeas was planted, and it actually germinated and grew. Now these two pipes are containing sandy soil. The one of the pipes has got atrazine. The other pipe doesn't have atrazine. But anyway, you can see in both the pipes we have got green plants, which means that when the herbicide was put on the sandy soil, it was completely leached out of the pipe. But on the red soil, you can see that one of the pipes doesn't have plants. This one where we applied the atrazine, you can see there's plants there. The controller has plants as well. So which means sandy soil leach atrazine. The red soils retain atrazine. This is the reason why the cowpea was killed. So we can easily demonstrate leaching using pipes. Number two, herbicides can be lost through volatilization. Now, volatilization is a function of a physical property known as vapor pressure. Now, what is volatilization? It is the physical change of a herbicide from solid or liquid straight into gas. 80 and 90% of the herbicide can be lost within a few days after application. Volatilization is a function of vapor pressure. So if we know the vapor pressure, we can tell to what extent the herbicide is going to be lost soon after application. We've got examples of herbicides with high vapor pressure. For example, EPTC, trifluralin, and clomazone, which is a command. These then are some of the examples of vapor pressure of the corresponding herbicides. This is measured in millimeters of mercury. Now, EPTC has got the highest vapor pressure, followed by clomazone, then trifluralin. Those with low vapor pressures are atrazine and the 2,4-D. Now, vapor pressure, because some of these herbicides can be lost, especially EPTC and the trifluralin. We may need to incorporate them in the soil. So EPTC and trifluralin have to be incorporated in the soil to avoid loss. So what you do when you spray, there should be a tractor spraying EPTC or trifluralin under dry conditions. Another tractor should be following with a disc. So you disc it in soon after application. It has to be disked in as you are applying it. Otherwise, it can be lost. Soil moisture displaces EPTC from adsorption sites. So we need to apply it under dry conditions. So EPTC is easily lost under moist conditions. So what normally happens is that when we have disked in these herbicides, normally if we get rains or irrigation, this herbicide is activated and it will start killing the weeds, because it can easily be released by moisture, which tends to displace the herbicide. The other issue is about 2,4-D in the form of ester, which is capable of drifting. Remember, we want the 2,4-D in the form of an ester so that it can easily cross the cuticle to enter the plants. But the downside is that such formulations can easily be lost because of high volatilization. So what can happen is that after applying the 2,4-D, it can be easily carried away by wind. So the formulation of an ester can actually increase the vapor pressure of the herbicide. So you can apply 2,4-D like at farmer A, then it can easily drift and affect farmer B because of vapor pressure. So I put a red flag on why we incorporate some herbicides like EPTC and the trifluralin. Biological processes. Now, biological processes involve plants which can degrade the herbicides or microbes. I know biological processes are the ones which enable us to understand selectivity. So some of the issues we could have talked about them under selectivity. Now, number 3 and 4, which is the role of plants and microorganisms. Remember on the diagram, 3 is the microorganism, 4 is the plants. That's why I've put 3 to 4. So plants and microorganisms are involved in enzymatic transformations of herbicides. It is the major route of herbicide detoxification in the environment. Metabolism, as we now know, involves 3 phases. For example, phase 1 processes, the initial properties of the herbicide compound is changed through oxidation, reduction, and hydrolysis. Production of more soluble and usually less toxic products than the original herbicide. So we produce something which is less toxic. Cytochrome P450 oxidative enzymes catalyze most of the reactions at this stage in both plants and microorganisms. And usually the functional groups such as OH, NH2, SH, and COH are added to the herbicide molecules. Of course, depending on the classification of the herbicide. We have been through this before. So I'll just summarize phase 1. It's like another revision here, where we have the activity of the cytochrome P450 catalyzing these reactions. For example, on this benzene ring, this is oxidation. We can have Cl, or even if we may not have a Cl, but OH is added to the group. There's also what is known as O dealkylation. If you have this structure here, so you will have ROH. N dealkylation, where you have got R, NHC3, where this is changed to NH2. Then there's something which we call oxidative deamination. Please remember there should be two nitrogen atoms joined together to this R group. And one of the NH2 is simply deleted, leaving one NH2. That is oxidative deamination. Then sulfoxidation, another name is thioether oxidation. There should be an S on the molecule, and we add oxygen. Nitrogen oxidation, we did not talk about this nitrogen oxidation, where oxygen is added to this structure. So please note, oxidation or phase 1 reaction facilitated by cytochrome P450, we are simply adding oxygen to the herbicide, so that we have the herbicide carrying oxygen, and we also produce water. These are the reactions, aryl or alkyl, or just call it hydroxylation. Second one, O dealkylation. Third, N dealkylation. Then oxidative deamination, sulfoxidation or thioether oxidation, and this one, nitrogen oxidation. Of course, we did not talk about this one. Again, where the cytochrome P450 is involved, the reduction or nitro reduction, where you have NO2 here, then we produce NH2 there. Hydrolysis, where we have an ester with this kind of a structure, then we produce RCOOH. Then we should have an amide, which has this structure. We can produce an amine. Nitrile has got these three bonds. We produce an acid there. You will see it later on when you go through your notes. So this is the phase 1. The phase 2. Now, in the phase 2, we have got three important compounds or substances. We have got combination of herbicide or herbicide metabolites with either sugar, number 1, amino acid, number 2, number 3, we have got glutathione. And these are known as conjugation reactions. The products have little or no phytotoxicity. If we have glucose conjugation to the herbicide, it can result in OS and N glucosides. In our case, we mostly talked about O and N glucosides. Uridine diphosphate glucosyl, UDPG, catalyze herbicide glucose conjugation reaction. It's an enzyme. Red flag, glutathione S transferase, GST, catalyze the glutathione and herbicide metabolite or herbicide conjugate reaction in plants. This reaction accounts for herbicide selectivity in several plant species. Glutathione is composed of three amino acids, glutamate, cysteine, and glyceric acid. Glu, cis, and gly. It's glyceric acid, sometimes we call it glycine. Which herbicides are affected by glutathione? We've got sulfonyl ureas, alloxyphenoxypropionates, triazine sulfoxides, and thiocarbamates. They can be affected by these glutathione. Microorganisms may not be involved in glutathione activities. So here we've got examples of conjugate reactions. We should have an ROH if we are going to form a glucoside. So you have glucose combining with this structure forming RO glucose. Any glucose, you should have this RNH2 combining with glucose. It forms RN glucose. If you have a glucose ester, you start with the RCOOH. Then you have this structure where you have R, C joined to oxygen, and also oxygen joined to glucose. Amino acid, you can have this RCOOH joined to this amino acid. Aspartate, we call it aspartate. But you can just write aspartate instead of writing this formula. Then glutathione may want to combine with the Cl position, where you have glutathione getting joined to this herbicide. Now, phase 3 reactions in plants and microorganisms. Processing of secondary conjugates which are non-toxic. Now we have herbicide sugar conjugates, which can undergo further conjugation with malonate via reaction of the malonyl coenzyme A. Final products are then moved into the vacuoles, or they may become part of the cell wall in the plants. But microbial conjugations could occur outside the cell. In fact, microorganisms can actually break herbicides further to CO2 and ammonia. So this is glucose, which can react to this glucose conjugate to form, glucose herbicide. This is malonate, where you have malonyl being joined to glucose. And then the herbicide ceases to be toxic. Now, microorganisms can further degrade the plants when they die. So when plants die, further degradation will take place due to microorganisms. We just want to pay a special attention to what they can do in the soil. Now, if we spray 2,4-D or any herbicide for that matter into the soil, there's what is known as the lag phase. Now, during the lag phase, nothing seems to be happening to the herbicide. In other words, there's no degradation for a couple of days because the microbes do not possess enzymes to degrade the herbicides. So, the contact of the herbicide with microorganisms may trigger synthesis of enzymes needed to degrade these herbicides. This can then be followed by rapid breakdown of the herbicide when there are now sufficient enzymes within the microbes. What can happen is that if we spray again that soil with a similar herbicide in the second season, the microbes will be ready to degrade the herbicide. So future applications of 2,4-D will be accompanied by a very rapid herbicide breakdown. In fact, the herbicide may fail to control weeds because of such rapid degradation. This could be typical for some soils in the USA where pre-emergence herbicides have lost efficacy. You apply the herbicide, it doesn't seem to work because of this reason. There's also something known as microbial activation, where phenylbutyric acids like MCPB and 2,4-DB could be activated by microbes via beta oxidation to produce MCPA and 2,4-D. We have got Pseudomonas species, Micrococcus species, Aspergillus niger, which can degrade MCPB and 2,4-DB, actually to convert them to herbicides. Now we move on to non-biological processes. So we move on to number 5. Remember, there are 7 processes we are talking about. We're at number 5, adsorption. Now, what is adsorption? We have ions and molecules which are electrically attracted to colloidal surfaces. So you have molecules of herbicides which are attracted to soil particles. The herbicide needs to be in an ionized state for it to be attracted to the surface of the soil. So the adsorption of herbicide ions and molecules occur specifically on the clay and organic matter surfaces. The herbicide molecules left in the solution are available for plant uptake or microbial action. So when we apply our pre-emergence herbicides, most of the herbicide is taken up by the soil clay content or organic matter. What is left is actually the one which can be used for killing weeds. If you look at the soil applied herbicides, pre-emergence herbicides, normally we base the dosage on clay content. There's an allowance for soil adsorption so that we have the, what is left to kill weeds. Now, there's also what is known as desorption. It is the movement of the herbicide ions from the clay and organic surface into the solution. It is the reverse of adsorption. So, adsorption and desorption are in a state of equilibrium. We can show this by this diagram, where we have got clay with the positive charges surrounding the clay and the herbicide with the positive charges being attracted to the clay mineral. And we may have some free herbicide in the solution. This is the herbicide which can kill the wheat. So when we base our rates or dosages, we have to take care of what is taken by the clay, and what remains should be sufficient to kill the weeds. And we can make adjustment by either increasing the dosage so that we can have enough to kill the weed. So adsorption and desorption are in a state of equilibrium. Now, if the herbicide has got a negative charge, it is repelled by the clay, and it can mostly be found in the solution. You have what is known as you have a movement from adsorption to desorption in this direction. Organic matter, but I must say that in our Zimbabwean soils, we do not have a lot of organic matter, but probably some soils in the temperate climates have a lot of organic matter. Nevertheless, let's see how organic matter can affect herbicides. So we have got the term sorption, which is used when the herbicide is taken up by the organic matter. So sorption is the partitioning of a non-polar herbicide into organic matter. So you have your organic matter and you have the whole herbicide moving inside the organic matter particle. Now, sometimes we talk of the KD value. KD value is the ratio of the amount of herbicide which has entered organic matter and the herbicide which is remaining in solution. That ratio gives us a KD value. In some countries, they use KD value to adjust the dosages. Another value can be KOC, KOC is the KD divided by the mass of organic matter. And it can also give an indication of the herbicide which is adsorbed, well, which is soaked by the organic matter. But in Zimbabwe, we use the clay content, not organic matter. So let us talk about what is known as ionization properties of the herbicide. Ionization is like you have components of the herbicide being dissociated from the molecule. Now we've got what are known as cationic or positively charged herbicides. These will be tightly bound to soil particles or colloids, because soil particles have got negative charges, and the herbicide will have a positive charge, and it will get attracted to the colloids. Now we've got examples of paraquat and glyphosate, which have no soil activity because they are tightly bound to soil colloids. These herbicides are very sensitive to quality of water, which is used for spraying. If you use dirty water, paraquat may not work or glyphosate may not work. So we have a loss of herbicide efficacy due to dirty water. And we've got also loss of efficacy when these herbicides come into contact with the soil. So this then is the paraquat. It has some positive charges. So if you spray it to the soil, it is tightly bound to the soil colloid or to particles of dirty water. However, with the glyphosate, there's a different type of arrangement on the soil colloid, because glyphosate itself presents a negative charge, but the soil colloid also have a negative charge. So what happens is that the soil particle could attract calcium if there's a lot of calcium in the soil, or it can attract iron. Now, the result is that, let's say the colloid is surrounded by calcium. Now, the calcium may not fully, it can fully neutralize this soil colloid, but there will be extra charges which are positive in such a way that the soil colloid will behave like like a positively charged particle. Then it will now attract glyphosate in the outer ring. So the inner ring could be calcium or iron. Then the outer ring is then glyphosate. Now, when we apply atrazine in the soil or some other pre-emergence herbicides. The efficacy depends on the soil pH. Now, at low soil pH 4.3, the atrazine molecule gains hydrogen ions at the 2 nitrogen positions in its ring. I will show you later on. This process is known as protonation. So protonation occurs under acidic conditions. This will result in a positively charged molecule of atrazine. So the atrazine charged molecule will be strongly attached to the negatively charged soil particles. Now, this causes atrazine to lose its herbicidal activity because it's tightly bound to the soil particles. And this is common here in Zimbabwe. The rate of breakdown of atrazine is also very fast at low soil pH. So we have got two situations: high soil pH and low soil pH. Now, under low soil pH, the atrazine molecule will gain hydrogen ions, these red hydrogen ions, and it becomes partially charged. Then it is attracted to the soil particles, and therefore it may not become available to kill weeds. So, like if you go into Chiota area where there's low soil pH, atrazine may appear not to be working. If you go to Buruwe or Chorocho, where you have a high pH, atrazine may be working very well due to this protonation. Less protonation in high pH, high protonation in low pH. So what is the effect of soil pH on atrazine efficacy? At soil pH above 5, atrazine is less protonated. Atrazine will be available in the soil solution. Increasing soil pH will increase atrazine efficacy. So sometimes limed soils make atrazine very effective in killing weeds. Here's an example of low soil pH. You can see atrazine is tightly bound to the soil particles. Under high soil pH, we are releasing atrazine from the soil particle, and this atrazine is free to kill weeds. Whereas under this situation, the atrazine is not available to kill weeds. Here's an example of interpretation of soil analysis using the pH calcium chloride scale, what we call very acid soils. They are below a pH of 4.5. And strongly acid soils have 4.5 to 5, and satisfactory for crop production you've got above 5. So here I've got a range of soils which were tested for pH. You can tell where atrazine is likely to do well. Chiota, can be problematic in terms of atrazine efficacy, whereas Wether with 7.6, atrazine can work very well. Bikita, you can see atrazine can work very well there. So atrazine is pH is very important in determining efficacy. We can actually reduce soil pH problems by liming of soils, or we can add cattle manure. The latter overrides the soil pH effect. So, on the issue of soil pH, on the activity of pre-emergence herbicides, especially atrazine, I put a red flag on that issue. Now, I want to talk about some weak forces of attraction, which are known as van der Waals forces. A weak attractive force among non-polar molecules. The molecule will have a zero charge. In fact, the molecule is not charged. So, soil pH does not seem to influence such herbicides with neutral charges like trifluorine. So, this is trifluorine. It is weakly attracted to soil particles by van der Waals forces. The molecule has got zero charge, and it is not influenced by soil pH. Another important issue I'm going to put a red flag is soil moisture. Because soil moisture can also affect the efficacy of herbicides. Water can compete with herbicides for binding sites on the soil sites. This could be important for EPTC. Herbicides tend to bind tightly to dry soils. So, under moisture stress, plants are unable to take the herbicide. Okay, so we have got a wet soil. This is the herbicide. Now, what happens is that water can surround the soil colloid and substitute the herbicide so that the herbicide is available. And under dry conditions, you have more of the herbicide surrounding the uh, soil particle, and there's less herbicide in the solution to kill weeds. So the addition of soil moisture can activate the herbicide. the herbicide will move into the weed zone. Adequate moisture ensures good weed control. Sometimes, if we apply herbicides under dry conditions, let's say after dry planting, you plant maize, you come in and spray pre-emergence herbicides like atrazine. If rains come 3 weeks later, the atrazine may be gone. So you may need soil moisture to make sure that the atrazine leach a bit so that it enters the soil. Now I'm going to talk about what may happen if you apply the soil on a dry soil surface. Again, red flag here, photo decomposition. Now, photo decomposition simply means destruction of the herbicide on the soil surface because of light. So, effect of radiation on herbicide molecules. These herbicide molecules should contain carbon and nitrogen in the ring to undergo photo decomposition. The wavelength, if you are interested, should be 290 to 490 nanometers, which can excite electrons of the molecules. The light can cause bond rupture, so you can have oxidation, reduction, hydrolysis, substitution, and isomerization processes being caused by light, and this can actually destroy your herbicides. Actually, this can affect most of the pesticides. And if we apply atrazine under dry conditions, this can happen to the atrazine. So atrazine may need to be leached a bit in the soil so that it is not affected by photo decomposition. Chemical decomposition. This is a straightforward reaction. You apply the herbicide to the soil, then there's going to be some reaction. This is a chemical reaction which could lead to herbicide degradation. No living organisms are involved. Soil pH determines the dissociation of herbicide molecules, so you can have hydrolysis, oxidation, and reduction. Triazines and sulfonylurea herbicides may actually undergo hydrolysis under acidic conditions. So this is actually the last process, but there are some issues which we may want to know concerning Zimbabwe. Now, in Zimbabwe, there have been some studies on herbicide persistence done by Chivinge and Mpofu in 1990. They used metallochlor and terbutylazine, atrazine, and prometon. They found that these herbicides could persist for 12 months in sandy soils. Zaranyika and Nyandoro demonstrated that the persistence of glyphosate was biphasic under aquatic conditions. What it means is that during the early part, there was fast disappearance of glyphosate, but it then tended to remain in the aquatic conditions for a long time. Other studies were done by Mushambi, where he found that the half-life of atrazine was 59 days for red clay soils. So on red clays, atrazine could stay for a long time compared to sandy soils where the half-life was 24 days. I will show you what the half-life is. So after herbicide application, if we measure the amounts after several months, we may come up with this curve. And half-life is, let's say you start with 4 liters per hectare. It could be heavy clays. The time taken for this dosage to reach 2 liters per hectare is what is known as the half-life. And it can give us an indication of how long the soil, how long the herbicide can stay within the soil after application. There's also a paper which looked at the persistence of atrazine in a maize soybean rotation under conservation agriculture. You may read it if you are interested, if you have the time. I'm not going to spend much time on it. I just want to focus on the factors which affect herbicide persistence. Why some herbicides may last a long time in the soil could be: number one, dosage. High dosages increase herbicide persistence, so calibration is very important. We need to reduce herbicide doses, so we can use herbicide mixtures in order to reduce the dosages, or we can apply bending if we want to reduce the problem of soil persistence. Number two, binding affinity. Herbicides that are strongly attracted to colloids are less available for microbial degradation, so they can stay in the soil for a long time. Clay soils have there could be long herbicide persistence, and in sandy soil there could be short herbicide persistence. Now, soil temperature and moisture can also contribute to persistence. For example, atrazine persistence can be 9 months in a dry season, but it could be 7 months in a wet season. So drought can influence, the persistence of these pesticides. High temperatures can increase degradation. In fact, in our soils, sometimes we tend to have a lot of herbicide degradation, especially in November and November, December, when it is very hot. There could be a lot of herbicide degradation. Soil amendments: if we add organic matter, cattle manure, these may decrease herbicides in the soil by adsorption, or they could promote microorganism populations which in turn degrade the herbicides. So these are some of the issues which may affect herbicide persistence. So I will just summarize what we have done under soil persistence by one slide. So when we talk about soil persistence, there are these 7 things listed on this first slide. It will summarize everything. So that's it. So I will stop.